Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the service mesh, the infrastructure layer that adds security, reliability, and observability to service-to-service communication without changing application code. We'll cover how platforms like Istio, Linkerd, and Console Connect use Sidecar proxies, mutual TLS, traffic splitting, retries, and the XDS protocol to tame microservices at scale. Whether you're preparing for a senior engineering interview or building modern cloud infrastructure, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the service mesh, the infrastructure layer that handles service-to-service communication in a microservices architecture. If you have ever wondered how platforms like Kubernetes, Istio, Linkerd, or Console Connect add mutual TLS, traffic splitting, retries, timeouts, and observability to thousands of microservices without changing application code, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building modern cloud infrastructure, let's get into it. Here is the core problem. A company starts with a monolith and then breaks it into dozens, then hundreds of microservices. Every service now needs to discover other services, encrypt traffic, handle retries, apply timeouts, split traffic for canary releases, and emit golden metrics. If each team implements these concerns inside every service, you end up with duplicated libraries, inconsistent behavior, language-specific bugs, and a security nightmare. One service retries too aggressively and overwhelms a failing downstream. Another service speaks plain HTTP over the public network. A third team ships a new version but cannot safely route only 10% of traffic to it. The platform team needs a uniform, decentralized infrastructure layer, a service mesh that sits next to every service, takes over connectivity, and gives operators control and observability without changing the application code. Let's walk through the functional requirements. First, the mesh must provide service discovery and load balancing so that clients do not hard-code addresses and can spread requests across healthy instances. Second, it must support traffic management capabilities such as weighted routing, canary rollouts, A/B testing, traffic shadowing, and fault injection for chaos engineering. Third, it must enforce reliability patterns including retries with back-off, circuit breaking, timeouts, and outlier detection that ejects unhealthy hosts. Fourth, it must provide security by default through mutual TLS, identity-based authentication, certificate rotation, and fine-grained authorization policies. Fifth, it must deliver observability by generating distributed traces, metrics, and access logs for every service-to-service call without instrumenting the applications. These 5 capabilities are the reason teams adopt a service mesh. Now the non-functional requirements. The service mesh must be transparent. Applications should not be rewritten and existing APIs should keep working. The data plane must add very low latency, typically sub-millisecond, because every request now flows through a sidecar proxy. The control plane must be highly available because if the control plane fails, configuration updates stop but existing traffic should keep flowing. The system must scale horizontally to support thousands of services and tens of thousands of proxy instances. Security must be zero trust. Every identity is authenticated, every call is encrypted, and policies are enforced at the proxy. The mesh must be interoperable with existing orchestrators like Kubernetes, virtual machines, and multi-cloud environments. And finally, the operational complexity must be manageable through declarative APIs, clear dashboards, and robust automation. Here is the high-level system architecture. At the bottom we have the workloads. Microservices running as pods in Kubernetes, containers on virtual machines, or legacy services. Next to each workload sits a sidecar proxy, the data plane component that intercepts all inbound and outbound traffic using iptables or eBPF redirection. The proxies talk to each other over mTLS and implement routing, retries, and telemetry. The control plane runs as a separate set of services that discover workloads, distribute configuration through the XDS protocol, issue certificates from a certificate authority, and push policy updates. An observability backend receives metrics, traces, and access logs from the proxies and renders dashboards, alerts, and SLO reports. The service registry, often backed by Kubernetes or Consul, keeps the mesh aware of where every service lives. The key metrics to memorize: cold data plane latency, usually measured as P50, P95, and P99 request latency introduced by the Sidecar proxy. Error rate, the percentage of requests that fail at the mesh level after retries, circuit breaking, and timeouts are applied. Mutual TLS coverage, the percentage of service-to-service calls encrypted and authenticated with mTLS. Traffic split accuracy, how closely actual traffic distribution matches the configured canary or A/B weights. Retry and circuit break events, which show how often the mesh is compensating for downstream failures. Golden signals including request rate, latency, errors, and saturation give operators a clear picture of service health. These metrics are what the platform team actually watches. Let's trace the end-to-end user journey. A platform engineer needs to onboard a new payments service to the mesh. She adds a label to the Kubernetes deployment, and the mesh automatically injects a Sidecar proxy into each pod. The proxy receives an identity certificate from the control plane certificate authority and begins accepting only mTLS traffic. The engineer configures a virtual service to send 90% of traffic to the stable version and 10% to the canary. She also adds retries, a timeout, and a circuit breaker. In the observability dashboard, she sees P99 latency, request rate, and error rate split by version. When the canary metrics look healthy, she shifts 100% of traffic to the new version. The application code never changed. The mesh handled discovery, security, reliability, and telemetry. The core models and algorithms. The Sidecar proxy is the fundamental unit of the data plane. It is a lightweight process that terminates network traffic, applies policy, and forwards to the destination. The XDS API is the control plane contract that distributes discovery data. Listeners, routes, clusters, endpoints, secrets, and extension configs. The workload identity model assigns a cryptographic identity, often based on SPIFFE, to every service and uses it for mTLS and authorization. The certificate authority issues short-lived certificates and rotates them automatically before expiry. Traffic policies model routing rules as weighted destinations, retry budgets, circuit breaker thresholds, and timeout values. Envoy health checking and outlier detection remove bad endpoints from the pool. The key trade-off is control versus overhead. A richer proxy adds latency and cost, while a thinner proxy gives fewer features. Now the low-level design deep dive. The Sidecar injection is implemented by a mutating admission webhook that patches pod creation requests to add the proxy container, and an init container that configures traffic redirection using iptables or eBPF. Each proxy maintains a local configuration cache populated by streaming XDS responses from the control plane. The control plane watches the service registry, transforms objects into XDS resources, and pushes incremental updates to subscribed proxies. The certificate authority issues service identities through SPIFFE URI SANs, stores them in secrets, and rotates them before expiration. The observability pipeline exports stats over HTTP endpoints, sends access logs to a collector, and propagates trace headers such as W3C trace context. Authorization policies are enforced by evaluating the source identity, destination identity, path, method, and custom headers at the proxy before forwarding the request. Key takeaways for your interview. First, a service mesh is a control plane plus data plane architecture, so always explain the split between the central brain and the local proxy. Second, the Sidecar pattern is the dominant data plane model, but Sidecar-less options using eBPF or per-node proxies exist and trade transparency for lower overhead. Third, mTLS and identity are the foundation of zero-trust networking, so be ready to discuss certificate issuance, rotation, and SPIFFE identities. Fourth, traffic management is the feature that unlocks progressive delivery, but it depends on accurate observability to avoid shipping bad canaries. Fifth, operational complexity is the biggest hidden cost of a mesh, so mention control plane upgrades, proxy resource quotas, and debugging tools. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the service mesh. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the service mesh. We covered the full picture from sidecar proxies in the data plane through the control plane, XDS, mTLS, traffic management, and the low-level design of proxy injection and certificate rotation. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.